Hi everybody, welcome back to the section 3.1 video. In this section, we're going to take a look at a Newton's law of cooling example and use it to figure out how long it will take for a cake to become room temperature. Okay, so let's go ahead and see what the question's asking. So a cake is removed from the oven. Its temperature is measured at 300 degrees Fahrenheit. Okay. So that means it's the initial temperature. And then it says 3 minutes later, its temperature is at 200 degrees Fahrenheit. So we're given a condition here that T of 3, meaning at 3 minutes, we have a temperature of 200 degrees. So now here's the question. How long will it take the cake to cool off to room temperature of 70 degrees Fahrenheit? So that room temperature, that's our ambient temperature or constant temperature, and that's our T sub M. And so we want to figure out the time it will take to get to 70 degrees. Okay, so we have a couple temperatures that we could fill out our Newton's law of cooling differential equation with that I can put in 70 for T sub M, our ambient temperature, and then we know our initial temperature is 300, so I can cross out and replace. So we know a solution to this dE differential equation is a Newton's law solution. So we know from the previous example and video that we established that the solution is T sub naught minus T sub M times e to the kt plus T sub M. We know that's the solution to Newton's law of cooling and heating. But we can replace a couple things now. We know what some of these constants are. It's 300 minus 70 e to the kt plus 70. Let me move this down a little bit, give us some space. Okay, so we know this for sure, and we can simplify a bit. We could have 230 e to the kt plus 70. Okay, so we know this is our solution, and the typical way to go about these models is we need to find K. We're going to use this K to figure out the time that's being asked. So let's go ahead and find K. So to find K, we want to use what is given to us. That at 3 hours, or excuse me, at 3 minutes later, the cake is at 200 degrees. So we're going to take 3, we're going to take 200 and plug it into the solution. So it'll be 200 equals 230 e to the k times 3 plus 70. All right, so let's go ahead and solve for k now. Let's subtract 70 to both sides. We get 130 equals 230 e to the 3k. Let's divide over by 230. So this would be e to the 3k equals 130 divided by 230. Gonna leave that exact for now. And we're gonna just take the natural log of both sides. Let's do it in the next step. So natural log of 130 over 230 equals the natural log of e to the 3k. So the natural log and e cancel out. And so what I'm left with is natural log of 130 over 230 equals 3k. So then we divide 3 over to both sides. Divided by 3. And so what we end up with is k is approximately, if you throw this in your calculator, 0.19018. So we take this k, we throw it back into our solution. Throw it back right in here. And we create our solution, and we're going to use this to figure out the time that the cake cools off to 70 degrees. But let's write the equation first. So the temperature of the cake equals 230 e to the negative 0.19018 T. Let me box that too. Okay, so let's go ahead and figure out the main question for this problem. So now we want the time T when this cake is at 70 degrees Fahrenheit. So we want basically T of T equals 7. Let's do it like this. Question mark, T of question mark, the time equals 70. So let's go ahead and figure that out. Let's plug 70 into our equation. Let's plug it in for the temperature. So we have 70 equals 230 e to the negative 0.19018 t. We're trying to solve for t. So, excuse me, plus 70. I forgot this even above. Excuse me. It should be plus 70. But let's go ahead and solve this now. So I don't know, let's subtract for 70 to both sides. Well, that would happen to cancel out on both sides. So we'll have 0 equals 230 e to negative 0.19018 t. Okay, so we'll divide 230 to both sides. Well, we'll just end up with 0 on the left-hand side again. Okay, well, we're trying to solve for t, so we need to get the t out of the exponent. So what if we natural log both sides? Okay, so the natural log cancels out with the exponential. And we're left with natural log of 0 equals negative 0.19018 t. All right, so good news, the t is out of the exponent, but we have an issue here. We cannot take the natural log of 0. That gives us no solution. Okay, so that's an issue. So we can't actually get the time it takes for the cake to cool off to room temperature. But what we can do is increment the room temperature a little bit to be able to get an approximate solution. So let's increment this from 70 degrees to like 70.5 degrees. So let's try 70.4 degrees. Okay, so same thing, we'll plug that into our solution. We'll plug it in let me come back up. We'll plug it in here, okay? Or here, if that helps. Doing the same process. So 230 e to the negative 0.19018 plus 70. Okay, so let's try the same way. Minus 70, minus 70. This is 0.5 now. So good news, we're not getting a 0. 230 e to the negative point. Okay, same thing. We're going to natural log both sides. So this will be natural log of 0.5 divided by 230 equals negative 0.19018t. And so, excuse me, typo. Sorry about that. Was going a little too quick. We will divide both sides by 230 first. Sorry. Okay, sorry about that. Then we natural log both sides. Natural log e to the negative 0.19018t. Natural logs cancel out. And I'm left with negative 0.19018t. Natural log is 0.5 to 30. Divide over that decimal. And so what we get is approximately 32.5 minutes. So doing the same work, just with a small incremental increase of 0.5 to 70.5, we actually get a time now. So therefore, it takes 32.5 minutes for the cake to cool to 70.5 degrees. Okay, we were asked for 70, but we went to 70.5 just so that we were able to get a solution. Okay, so let's scroll up to the table here, or the graphs here. And here's a visual A that we start out at 300, but then after like 30 minutes, it gets to a constant ambient temperature of the room 70. And then a table here that, we couldn't get 70, but we were able to get 70.5 and it's a close 32.3. Just a bit of rounding here and over there, but yeah, so that's how we would do one of these Newton's laws. So a couple key things to remember is that we know for a fact that this will be the solution to a Newton's problem, okay? And depending on what the problem gives us is how we take it from there. But we always want to find K, and then we're always asked to find some time. Okay, that's it for this video and this section. Thank you for watching. I will see you in the next one. Okay, take care.